This is lecture 2 for continuous modeling. Um, we'll look at some of the more details of building models using the continuous portion of OSM. Um, we've already talked about modeling using state variables, and that's kind of the essence of continuous modeling. So you need to write function state, and you can have any combination of what's called DD and SS variables. So SS variables are the state variable, but you can express it either as an SS equation or what's called a DD equation, which is the derivative of the state variable. Um, Another way to express these variables is something called difference equations. And difference equations simply refer to the current value and the y minus n value, or y of n minus 1 value rather. So SS1, if you take this approach, is the current value or y sub n value, and SSL of 1 is the last value, or the y of sub y of n minus 1. So if we have an equation for the state variable, it's a function of the previous value times some rate and some constant. We can express that as SS variables in the form of difference equations. And so SS1 is equal to this coefficient times the last value plus whatever the constant is associated with this equation. This is a faster way, doesn't require integration to compute the new value of SS1, and so it runs quite a bit faster. So if you're able to express models in this form, they're very efficient. We can do higher order difference equations by using combinations of SS1 and SS2 variables. So for example, if we have a higher order equation like this, where y sub n is really a function of y sub n minus 1 and y sub n minus 2. So we set SS1 to y sub n and SS2 to y sub n minus 1, and we're able to come up with an expression for SS1 as a function of SSL, which is y sub n minus 1, and SSL of 2, which is the previous version of y sub n minus 1 or y sub n minus 2. We link the whole thing together by expressing SS2, which is y sub n minus 1, as SSL of 1. Okay. So by defining these two equations in this manner, they're kind of linked together, and we're able to compute SS1 as well as SS2. Derivatives of state variables is the second way that we calculate changes in the values of the state variables. And OSM uses a Runge-Kutta-Feldberg algorithm to do the integration. So this is kind of an approximation method, although it's very accurate. It involves stepping time forward in small time steps and estimating the possible error that might occur based upon previous rates of change of the various variables. So it's used to basically obtain the solution of a set of simultaneous first order ordinary differential equations of this form. So we can express a state variable as a derivative, which is a function of other state variables in the system. So at SLAM, this is expressed as follows. The DD variable is the derivative of the state variable, and it's a function of all of one or more of the other state variables plus t now. So for example, if we have a derivative of y equal to ay1 plus by2, and the second variable, a derivative of y2, with this expression, in state we can express that in this form. So dd1, which corresponds to this derivative, is equal to a1 times ss1 plus b1 times ss2, and same thing for dd2. We can also put equations in canonical form and express higher order derivatives. So the second derivative of x with respect to t might have this form as a function of the first derivative and the variable itself. So if we let ss1 equal the variable x of t, dd1 can be the derivative of x of t. And we'll also equate that to ss2. So then the derivative of ss2, which is dd2, is this second derivative. So in function state, we can express it in this manner and handle higher order equations. Most applications are fairly straightforward and don't involve all of these different derivatives. Um, Another variable that you should be aware of and be careful in its use of is dt now. It's the value of the time increment which SLAM is using to update the state variables over a full step size. So dt full is the size of the step that's being attempted. In many cases, dt now equals dt full. However, if two events occur at the same time, then the second event processing involves dt now equal to 0, since we don't want to advance time, but we have two events that may occur at the same time. Say some state event where there's instantaneous change in the value of the state variable. So if this is the case, we don't want to use dt now as a denominator in function state, because we'll get a division by 0. Okay, but it should be used in an equation in which the state variable is updated by a rate multiplied by the increment in time. So here's another way to represent how state variables change. We can take the previous value and then look at the time increment that we're trying to update over, which is dt now, times the rate. So this portion of the equation tells us how much the SS variable is changing, and it's added to the old variable that we established in the previous step attempt. And the sum of those two gives us the new value of SS1. So in this case, you should use dt now, but just be careful if you have any situations where dt now would be used as a denominator. Okay, that's the end of the continuous modeling second lecture, and I encourage you to investigate the examples in the textbook and try exploring these features further.